Invented in the 1930s, synchrotrons and particle accelerators have already defined the world we live in. A product of a particle accelerator is right in front of you. The laptop you are watching this on uses semiconductors and electronic pieces that particle accelerators specialize in making. The most famous use, of course, is the Higgs boson, but initially particle accelerators were only used in the interest of identifying the atomic structure of a nucleus. There are many types of accelerators developed and in use today, but they all fall into two main categories: circular accelerators and linear accelerators. A linear accelerator uses its length to apply a constant acceleration onto a particle, so to increase the speed of a particle you need to increase the length of the accelerator. Circular accelerators have the large benefit of being able to increase to significantly higher speeds in a fraction of the space, as the particle can benefit multiple times from looping around the accelerator. But the added complexity in creating them means that they require a significantly higher budget. Circular accelerators are also crucial for atomic structure, as they allow for two beams of particles to collide in an enclosed environment. The various types of accelerators are listed here. Ion implanters, used to reinforce materials from wear and damage through surface hardening, to fabricate semiconductors and to produce medicinal implants. Electron beam accelerators. They are used to make materials resistant to chemical reactions, pathways, and extreme temperature by strengthening bonds. The electron beams also function as a sterilization method for disinfecting medicinal products, food products, and sewage. They are used widely in the automotive and aerospace industries, machine construction, and medical product manufacturers. Linear accelerators. Beyond their main use of atomic analysis, linear accelerators are designed for hospital use, for treating tumors and cancer therapy. Cyclotrons. They are often built into hospitals, producing safe, medicinal probing and treatment radioisotopes. Electrostatic accelerators. Used to investigate material properties, monitor the environment, support biomedical research, and study cultural heritage objects. Finally, synchrotrons. They are the largest and most significant particle accelerators of all time. Both the Large Hadron Collider by CERN and the Australian synchrotron by ANSTO are large-scale multi-purpose synchrotrons. The range of synchrotron applications is so significant that we first have to understand the accelerators themselves. How does the Australian synchrotron and other particle accelerators work? So quickly, let's have a look at the basic steps that apply to all particle accelerators. Step 1. A particle is generated and accelerated at the gun component. Step 2. The linear accelerator speeds up the particles and focuses them on a point. Step 3. The booster ring increases the speed and energy of the particles. For synchrotrons, which use electrons as their particle. Step 4. The storage ring continuously accelerates electrons to create synchrotron radiation. Step 5. The radiation and synchrotron light is piped down beamlines, which take the light to experimental workstations. For colliders, which use protons, heavy ions, and neutrons. Step 4. The storage ring continuously accelerates the particles, colliding them with the target or other beam. Step 5. Detectors watch the interactions and determine the results based on diagnostic, quantitative, and qualitative data. So let's go over the steps one by one. With respect to the Australian synchrotron owned by the Australian Nuclear Science and Technology Organisation in Clayton. In step 1, the particle gun generates the particles from a source. In the current context, that source is a tungsten matrix cathode, with a large voltage applied across it. This causes the electrons to heat up the material, attempting to jump from the cathode to the anode across the vacuum. Once the cathode reaches great enough energy, the electrons jump off and are accelerated. The Australian synchrotron applies a 500 MHz signal to its supply, which causes the electrons to fire in bursts, 2 nanoseconds apart. The large potential difference with the gun allows for the electrons to be accelerated. The Australian synchrotron uses a 90 kilovolt power supply, so the electrons reach 90 kiloelectronvolts. Before we move on, I need to discuss the unit you just saw. An electron volt measures the energy of a particle. 1 electron volt is the energy gained by an electron that accelerates through a 1 volt electric field. The Large Hadron Collider reaches a 6.5 tera electron volts. In everyday terms, this is a ridiculously tiny energy, roughly the energy of a safety pin dropped from a height of just 2 centimeters. Despite the amount of energy, the concentration is so extremely high it compares to the concentration of energy that persisted moments after the Big Bang. Step 2, and the bunches of electrons have arrived at the linear accelerator. This machine is a long tube spanning about 10 meters. It contains a series of radio frequency cavities. These cavities resonate at specific frequencies through the use of alternating electron fields. This causes the generation of radio waves, which are at the perfect frequencies to interact with nearby bunches of electrons, imparting their energy onto the bunches, accelerating them. The Australian synchrotron accelerates the electrons with a 3 GHz frequency, which applies 100 MeV to a bunch over the 10 meters. The linear accelerator can only accelerate a beam once a second, but within the first meter of acceleration, the electrons are already traveling at more than 99.99% of the speed of light. Step 3. The bunches enter the booster ring. For a sense of scale, the Australian synchrotron's booster ring is approximately 130 meters in circumference. The goal of the booster ring is to both accelerate the electron bunches, but to impart a high enough energy for either collision or creation of synchrotron radiation. This requires the booster ring to impart a significant amount of energy upon the bunches, which it does by using radio frequency cavities operating at 500 MHz, with 5 distinct cells within. Around the ring, 60 electromagnets are used to both steer and focus the beam, as well as impart energy onto the bunches. As a reminder, in all of the steps so far, the use of a vacuum chamber is extremely important, as air molecules block both the acceleration of the beam, but cause it to deflect off course. This would prevent the usage of the accelerator due to its crucial requirement for fine and focused electron beam, with what we call an extremely small divergence. Due to the lack of air molecules and the use of those magnets, the beam is reduced to a path 60 micrometers in width, with an orbit deviation of less than 5 micrometers. In comparison, a human hair is typically around 80 micrometers wide. The Australian synchrotron increases the velocity of the electrons by increasing the magnet strength and the strength of the cavity fields, increasing the energy of the beam to 3 GeV. Each ramping cycle takes approximately 1 second for a complete ramp up and ramp down. An electron spends about half a second in the booster ring and completes over 1 million laps. The electron beam's velocity reaches to approximately 299,792 kilometers per second. The electron then enters the storage ring in step 4, which is approximately 216 meters in circumference, split into 14 sectors. Each sector contains a 4.4 meter straight section and an 11 meter arc. The arcs contain 2 dipole-dipole magnets, which bend the electrons. As a result of this bending in such a small space, the electrons going at incredibly fast speeds shed some energy to complete the arc. The energy is released in the form of photons with varying wavelengths of light. The photons continue on in the direction they were going in before the arc, called the tangent velocity or tangent direction. It is also important to note that the more energy a particle has, the greater the magnetic field needed to bend its path. We will come back to the light later, but it is important for note that within the storage ring, the straight sections of each sector leave room for a sample or device to be inserted that can change the properties of the radiated light, or provide a target as an impromptu collider. The storage ring contains 6 quadruple and 7 sextuple magnets, giving a total of 84 quadruple and 98 sextuple magnets in the storage ring. These magnets are used to correct the beam, its orbit, its divergence or width or focus, and the wavelength of the light released when passing an arc. Quadruple magnets specialize in focusing the beam and lowering the divergence, while sextuple magnets specialize in modifying the orbit and the beam. Next, the synchrotron radiation enters beamlines, which are long lines that capture the photon beams and manipulate it for later use. Each beamline can change how the light varies through the use of filters, monochromators, mirrors, attenuators, and other devices. This allows a researcher to select a specific set of wavelengths for their designated use case or scenario. Finally, the synchrotron has end stations, which are experimental workstations that use the synchrotron light from the beamlines. They are contained in lead shielding to protect against the penetration of synchrotron light affecting users outside the workstation. The synchrotron light is used to gather a form of quantitative or qualitative data through images, chemical or emission spectra, and scattered light. Because research scientists cannot enter the hutches during data collection, much of the equipment is controlled remotely via motors and robotic devices. Earlier, I discussed the energy level of 3 GeV. This was specifically chosen, along with the varying magnetic acceleration methods, to generate the following spectra of photons from synchrotron radiation. The graph illustrates a wide range from infrared to hard X-rays. Now let's discuss the two main magnetic manipulation devices used in the storage ring: wigglers and undulators, the main insertion tools used within the synchrotron. These are inserted into the 4.4 meter straight sections with the goal of amplifying frequencies of light. A multipole wiggler, or MPW, which uses many high-powered alternating magnets to create many spanning cones of synchrotron light by bending the path of the electrons back and forth rapidly, which superimpose the intensity increasing with the number of bends. They are used to reinforce spectrums of light, creating a broad beam of incoherent light. The second device is an undulator. It keeps the same alternating magnets but with less power and at larger intervals, causing gentler ripples in the electron bunches, and thereby gentler changes in the synchrotron light. The cones of coherent light produced by the undulator superimpose and interfere in such a way that certain wavelengths of light are enhanced by perhaps 10,000 times. By varying the gap between the magnets, the wavelength that gets amplified can be tuned to a specific value. The undulator also keeps the beam narrow, whilst the wiggler widens the beam. So we need to talk about the characteristics of synchrotron radiation propagation. Whilst the math from synchrotron radiation theory is complex and ultimately irrelevant to the understanding we require, parts of the radiation emission are crucial to understand before moving into the characteristics of synchrotron light. The following is taken from the theory of synchrotron radiation by Helmut Weidmann in his research publication, Particle Accelerator Physics. The radial ellipse shows the path of the radiation between two major angles, here theta and phi. As the beam of electrons bend round the synchrotron, tangent beams, all with approximately similar angles, are released from the bunches. With the assumption that these angles are extremely small, we can derive for the angle based on the wavelength of light. If we assume phi is 0, and we use the approximate trigonomic identity for cosine, cos theta approximately equals 1 minus a half theta squared, for extremely small values of theta, along with the formula for the approximation of energy in photons, beta equals 1 minus a half wavelength squared, we can find a derivation for the approximate scaling of radiation intensity, where k equals the wavelength to the power of negative 2 plus theta to the power of 2, all to the power of negative 3, giving an emission angle of theta equals plus or minus 1 on lambda, or 1 on the wavelength. Plotted against intensity, we can see the amplitudes of radiation peak at the smallest values, which is what gives synchrotron radiation its unique intensity. We can also see these values drop off as the angles start to increase. This figure illustrates the tangential lines of synchrotron radiation, representing a circular particle accelerator. The paper also notes that the extreme collimation of the synchrotron radiation and its high intensity and high energy electron accelerators can cause significant heating problems, as well as desorption of gas molecules from the surface of the vacuum chamber. This is attempting to describe that as the energy of the synchrotron increases, the radiation power itself rips apart the atoms on the wall of the vacuum chamber, so powerful radiation shielding is required when the synchrotron is active. Waves. Whilst we talked about them being defined by their wavelength and amplitude back at the start of the year, they are also defined by their energy. In the atomic sense, these waves are treated as particles, so their energy defines a significant amount of the synchrotron radiation properties. More specifically, its use in chemical relations. Due to the photon to chemical bonds interacting, a specific wavelength of radiation would be able to penetrate the bond by overlapping the binding energies of valence and core electrons in solids and molecules. These waves, as discussed back at the start of the year, contain both magnetic and electric fields perpendicular to each other. This allows for a wave to be described by waveform functions such as the ones you see on screen, which we did use in the previous section. Whilst they aren't necessary to understand for our investigation, due to the scale the experiments are taking place on, these functions introduce Heisenberg's uncertainty principle in relation to the momentum of the waves. So the use of undulators and wigglers before effectively shrink wavelengths with relativity by acting on the high energy electrons that move longitudinally. This further illustrates the importance of undulators and wigglers, as they allow for the radiation to be generated in the first place, or risk uncertainty principle causing large failures. So let's take a step back and reiterate. The electrons in the synchrotron are going 299,792 kilometers per second. As they rotate around the center due to the dipole magnets, the tangent velocity flings off radiation in the form of photons. These photons are filtered and adjusted through varying insertion devices like bending magnets, wigglers, and undulators to modify the light when needed by differing experiments. The light created is so intense that the light produced by the Australian synchrotron is as bright as 1,000,000 suns. As such, the light must have some extremely unique properties which determine its characteristics. The synchrotron light is intense, hundreds of thousands of times more intense than that from conventional X-ray tubes, and has an extremely low divergence, or theta angle from the section before. Synchrotron light is variable for differing experiments, not requiring a new machine for a new wavelength, has a long range of light wavelengths to pick from. This is due to the wide wavelengths of light that the synchrotron produces inherently. The emitted radiation is also customizable, allowing for varying experimental usages that conventional X-ray or laser light cannot provide. Whilst not as significant, the radiation is emitted with extremely small time differences, a billionth of a second, allowing for experiments which take into account time as quantitative data. Synchrotron radiation releases into a small angular fan, which creates the large intensity and collimation unobtainable in conventional laboratory sources. This graphic on the left here shows the intensity of radiation over its wavelength, common to all dipole radiation. Hard radiation can penetrate most matter, while soft cannot, allowing for specific experiments over a range of wavelengths. This diagram here on the right illustrates the radiation horizontally polarized, as produced by the average synchrotron. The radiation's very controlled nature allows use in both diffraction experiments and spectroscopy. From this information, we can gather a few more unique properties of synchrotron light. The high collimation and low divergence causes a significantly stronger beam of light, but also prevents its loss during the transformations before reaching a workstation, resulting in greater eventual resolution in measurements due to its spatial precision. And synchrotron light produces a smooth and continuous spectrum, allowing for much greater range of experiments, rather than the singular wavelengths other light sources can provide. So how do these properties differ from the properties exhibited by conventional laser light or X-ray sources? Laser light conventionally falls between infrared and ultraviolet, mostly within the visible light spectrum. Laser light is monochromatic, coherent, strong in wavelength, and has a low divergence. X-rays from X-ray tubes produce their light through the same principles that synchrotrons do, by using thermonic emission to generate electrons and shooting them into a target. 1% of the energy is converted into perpendicular radiation, the rest into heat. The metal the electron hit determines the wavelength and has a very short spectrum, much like laser light. There are filters to remove most inconsistencies, but the light is still a small spectrum of mostly collected beams of radiation. Synchrotron radiation outperforms both almost 1 billion to 1, literally. A synchrotron source has a brilliance that is more than 1 billion times higher than any laboratory source. The brightness of a beam and its angular speed is the light's brilliance. Brilliance is used to compare light sources, where a higher brilliance allows for the higher resolution or level of detail in a studied material. It means effectively that there is a greater precision where brilliance is significant and recorded by a detector. Synchrotron radiation can penetrate matter, has a significantly longer selection of wavelengths with the ability to pick and choose, higher energy, extremely low divergence, is coherent, reinforced, and polarized. It allows a practitioner to perform every experiment they could have with conventional equipment to both a higher degree of resolution and with a greater range of parameters. Synchrotron radiation also allows the experiments normally impossible to become impossible. The unique properties of synchrotron radiation provide it with remarkable analytical capabilities for the characterization of materials. Due to the aforementioned properties of brilliance, customizability, tunability, and wide electromagnetic wavelength, synchrotron light has extensive experimental usages. In chemical analysis, spectroscopy techniques with synchrotron radiation can be used to determine functional groups, molecular structure, composition, emission, speciation, and coordination site analysis. It has uses in structural analysis through its advanced wavelength capabilities, used to comprehend the modifications to the material made through X-ray diffraction, small-angle X-ray scattering, and X-ray reflectometry. Synchrotron radiation is used to understand electronic and magnetic properties, especially relating to the surface of a material. It provides a large insight into the observation of atomic structures through soft X-ray emission, photoemission electron microscopy, angular resolved photoemission spectroscopy, low-energy electron microscopy, and X-ray magnetic circular dichroism, and morphological characterization, which refers to the visualization in 2 or 3 dimensions of very fine details of complex structures. All of these uses are a direct result of synchrotron radiation properties. All of these are extremely important experimental techniques that could never have been developed or used to shape our developed world today without the use of synchrotron radiation. Which leads us quite nicely into applications of particle accelerators. To put it simply would be an injustice, but given the length and extent into which I've done the rest of my research, I feel that summarizing applications to an applicable standard should suffice. Synchrotron radiation is primarily used for the study of properties in condensed matter, normally impossible to study due to various chemical reasons, or for a higher resolution study of properties in any form of matter. To quote IAEA again, synchrotron radiation studies condensed matter, nanomaterials, molecular and atomic processes, biological systems. In particular, femtosecond X-ray pulses are used for the single bunch timing experiments that are able to unlock exotic research capabilities into the ultra-fast and high-resolution scale of molecular and atomic dynamic processes. I will first summarize synchrotron radiation usage to end the previous section, and then refer to the applications of both collisions and synchrotron radiation in a higher level of detail, before ending on one of the greatest scientific discoveries ever made by a synchrotron. Currently, the Australian synchrotron in Clayton uses the radiation for the following experimental purposes. Whilst most synchrotrons are used for a variety of reasons, which we will get into later, the Australian synchrotron limits itself to purely research. Within the category of crystallography, the study of crystallized structures, high-performance macromolecular and microfocus analyses can be made with the high intent and brilliance and variability of synchrotron radiation, allowing for a deeper understanding of lattices and their interactions. Within light diffraction, they perform powder diffraction, used for analyzing unknown crystalline and organic materials, and advanced diffraction and scattering, used for the extensive variety of light scattering purposes in research for both chemistry, physics, and quantum physics. Scattering also contains biological scattering with low divergence and wide-angle scattering for a larger range of research applications. Within imaging, medicinal imaging and radioisotopes are used with microcomputed tomography and various other products to produce a safer and more extensive health visit. Within microscopy, synchrotron light is used for nanoprobing, X-ray fluorescence, THZ far infrared, and infrared microscopic purposes, impossible with normal electron microscopes. Spectroscopy, as discussed earlier, is a very important part of analyzing structures of chemical bodies, which the radiation is adept at performing. Briefly, I'll talk about specific particle collision applications: making semiconductors through surface treatment of electronics, medical imaging and cancer treatment, producing radioisotopes, probing and destroying, sterilizing food and medical equipment by obliterating everything in the beam's path, oil and gas drilling efficiency, making polymers and ceramics for wide-scale consumerism. And finally, let's go over the joint applications of particle accelerators for synchrotron light and collisions. Making shrink wrap used in electronic safety devices, making computer chips, modifying material properties, that includes altering plastics, surface treatment of materials, medical sterilization and pathogen destruction, hardening for semiconductors and making artificial prosthetics, inspecting nuclear fuels, so that's cargo inspection with free electron lasers, the production of radioisotopes for medical diagnosis and therapy, so that's isotopes that emit rays or positrons are used as probes. This allows the outside world to see the biology inside based on how the radiation diffuses. Isotopes that emit electrons or alpha particles are used for cancer cell destruction. Microwave linear accelerators producing electron beams and X-rays are used for this exact purpose. Sources of beams of electrons, protons, and heavier charged particles for medical treatment is also an application of particle accelerators. A really amazing research paper by CERN from the 1990s talks about many of the applications in great depth, but I will summarize them here briefly as I feel the paper iterates on the true extent of accelerator usages. research into particle physics, including quarks, leptons, and bosons, research into nuclear physics. That means understanding superdeformed nuclei, spectroscopy of nuclei, understanding exotic unstable nuclei, understanding nucleus collisions and fragmentation, researching subnuclei degrees of freedom, study of nuclear matter under extreme conditions, converting nucleons to quarks and gluons. In astrophysics, it's possible to study the points in heat of time where W and Z bosons gained mass and vanished. Results obtained with accelerators have made it possible to explain cosmic observations such as the helium-hydrogen ratio and to determine the number of neutrino families. Nucleosynthesis in stars is also researched, and stellar reactions with high-powered beams of energy. Now, atomic physics, which I have directly quoted here, mechanics of atomic collisions and ionization processes, charge distribution and rotational properties of electron clouds during collisions. So this is research into correlation effects in atomic collisions, the study of highly excited atomic states produced during atomic collisions, researching into the physics of highly ionized ions and of bare atoms, research into charge exchange cross-sections of high velocity or even relativistic ions, so that's electron capture and electron losses, understanding X-rays produced by ion collisions, researching quasi-molecular states produced by symmetric ion-atom collisions, electron impact ionization processes and electron-ion collisions. This is very important for plasmas and did end up being very important for later research into radiation. Electron emission following faster ion impact on thin solid targets in view of quantitative analysis of surface contamination. Resonant transfer and excitation in ion-atom collisions. So this is the effect due to resonant capture of a target electron by the projectile ion and the subsequent excitation of that ion. Production of convoy electrons, which refers to electrons ejected in ion-atom and ion-solid collisions, and then matching their vector velocity to that of incident ions. Precision ion energy loss in solids, precision range distribution and electron stopping powers in solids, and the study of molecular ions. Matter and material sciences include probing structures and identifying properties of solid materials, and the spectroscopy on solids. Spectroscopy through synchrotron radiation. Elements absorb a particular spectrum of light more than others, which allow you to attain the structure of the material through extended X-ray absorption fine structure, which also gives you the atomic arrangements for later identification. Neutron scattering, understanding semiconductors, bonding, cohesion, and insulation. This includes neutron diffraction, which is used in physics and chemistry as properties. Rutherford backscattering, proton incident X-ray emission, charged particle activation analysis or nuclear reaction analysis, secondary ionization mass spectrometry, particle desorption mass spectrometry, which I've pulled directly, but you can see it elucidates on how many different forms of spectroscopy are possible through material and matter sciences. Further applications relating to chemistry and biology, more specifically synchrotron light, can be used for spectroscopy of chemical states and structures. That's oxidation, bonding, absorption layers, structures, dynamics, and kinetics. Radiation-enhanced chemical reaction analysis can be taken place. Pathways of radiation damage and cancer treatment can also take place under research. Crystallography of proteins, viruses, and ribosomes. In current history today, ribosomes have actually been resolved to a higher resolution with a synchrotron. Dynamics of biological and tissue interactions can also be researched. Under element analysis, rock and geological analysis, which is good for meteorites. We've got carbon dating, locating hydrocarbons under the ground. Nuclear reaction analysis, so that's finding compositions of old materials and pigments and minerals. And detecting concealed explosives. Under medicine, we've got diagnostics, so that's a bit like the barium tests that are in use today, but to a much higher accuracy. It's X-raying to a radioactive probe material inside the human. We can produce better responding radioisotopes, more specifically positron emission tomography, which uses low radiation and has a short life, but has a much stronger response. and we've got increased sensitivity X-rays. Also under diagnostics, we've got making superconductor magnets for NMR machines. In therapy, radiation treatment with synchrotron light and gamma ray linear accelerators, linear energy transfer to a high degree of resolution, isolating cancers with accelerated protons and heavy ions, and safe tumor therapy. Under industrial processing, we've got ion implantation for making semiconductors, making very small circuits, modifying the properties so that surface hardness, corrosion resistance, friction, fatigue, adhesion, and catalyst behaviors of materials, strengthening high tension materials, and making strong artificial prosthetics. Under radiation processing, more specifically exciting and ionizing materials, we can increase the rate of polymerization by a factor of 100. We can modify wood to improve fire and biological resistance. We can cross-link polymers to prevent solubility with organic solvents. This is used with polyethylene pipes and insulated wires and cables operating in hard environment conditions, high temperature, aggressive chemical media irradiation, making thermo-shrinking plastics, making modifications to rubber, so that's heat resistance and deformation resistance, chemical bonding polymers and substrates for curing paint and varnish, creating textiles with specific properties relating to fire and water resistance, splitting molecules to destroy unwanted materials, and purifying gases by passing on energy to create catchable salts, like ammonia from nitrogen oxide. Finally, under food preservation, we have radiation sterilization, suppression of microorganisms in fresh foods, extending life by 1 to 2 weeks, and crop protection, that's insect sterilization with the radiation from the beams. And finally, it's 1964. Peter Higgs is working on quantum field theory to explain weak nuclear force present in all matter and what gives matter its mass. Quantum field theory describes all matter as existing in fields, and different forms of matter existing as different forms of energy in a certain field. CERN used the example of the photon, which is a wave in the electromagnetic field. The photon illustrates another important part of quantum field theory, being the passing of energy through interactions. When two electrons interact, they exchange a photon. Quantum field theory prohibits the existence of the weak field, as it illustrates all matter without mass. W and Z bosons are the respective particles for the weak force interaction. If these particles functioned as quantum field theory states, they would be massless. In layman's terms, W and Z bosons require a mass to be able to have their range of effect. The laws of nature require all equations to be symmetrical, as otherwise the equation cannot be solved. So Higgs developed the Higgs field, which would avoid the laws of nature by using spontaneous symmetry breaking to give the bosons mass. It describes that the system must be both initially and constantly symmetrical, but can break for an instant. Think of a pen on a table. If balanced perfectly, it will still choose a direction and fall in that direction. Symmetry was present, but only initially. When the universe was born, it was filled with the Higgs field in an unstable but symmetrical state. A fraction of a second after the Big Bang, the field found a stable configuration, but one that breaks the initial symmetry. Because the laws of nature aren't violated by an unintentional unsymmetric equation, the Higgs field gives mass to not only the W and Z bosons, but all particles. Quantum field theory represents every particle as a wave in a field, as discussed before. As because there is now a new field, there must be a particle associated with this field, the Higgs boson. Think of this new field like a 2D grid, where a particle enters the grid, it gains a standardized mass based on the interactions inside the field. The Higgs boson is the second heaviest particle, but has an extremely short lifetime. According to CERN, approximately 10 to the negative 22 seconds. Describing this as looking for a needle in a haystack would be an understatement, as it is virtually impossible to detect or observe in that short of a time frame. CERN's Large Hadron Collider detects the traces that the boson leaves behind when it decays, but due to the products of the decay being the same as the products of colliding two particles, it's hard to tell if the boson was created in the first place. So instead, the accelerator measures deviations in mass per event per electron volt, and determines over a large distribution curve if the theoretical mass of the Higgs boson matches the peak of the curve, which it did on the 4th of July 2012, proving that the Higgs field existed. And that marks the end of your newfound intense understanding of the components in particle accelerators, their usage, applications, and most importantly, a greater understanding of the properties of light in an experimental vias.